Hello everyone. So this is a question from JEE Mains 2026, 28 Jan morning. So they have given us two statements. The first statement is number of pairs from following in which both ions are colored. Okay, so this is a important that we have to choose those ions which are colored and both the pairs. An aqueous solution is 3. Okay, so they have given us pairs: scandium plus 3, titanium plus 3, manganese plus 2, chromium plus 2, copper plus 2, zinc plus 2, nickel plus 2, and titanium plus 4. Okay. Statement 2. Thorium plus 4 is strongest reducing agent among thorium plus 4, cerium plus 4, gadolinium plus 3, and europium plus 2. Okay, so we have to choose the strongest reducing agent. Strongest reducing agent, and we have to tell which statement is true, which statement is false. Okay. So we need to talk about color because the first statement is related to color. Okay, so color is due to presence of incomplete d subshell. Okay, it's due to presence of incomplete d subshell, yeah, d orbitals. Okay, so what happens is, let's say we have a transition metal ion, so x of plus n. So when the ligands approach the transition metal ion or the transition metal atom, so what happens is, in this process, the d orbitals of this central metal atom, they split into T2G and Eg. Okay, earlier they are degenerate, or in the absence of ligands they are degenerate, that is all five of them, that is dxy, dyz, dzx, dx square minus y square, and dz square. All of these guys have the same energy in the absence of ligands. That's why they are degenerate. But the moment ligands approach them, they split into two, that is T2G and Eg. And Eg has higher energy and T2G has lower energy. So electrons can jump from lower energy d orbitals to higher energy d orbitals, and the amount of energy to do this transition for this electron to jump from T2G to Eg is obtained by absorption of light in the region of visible light. Okay, this is very important. Amount of light, amount of for electrons to jump from lower energy d orbitals to higher energy d orbitals, required amount of energy to do this is obtained by absorption of light in the region of visible light. Okay, this is a very important statement. That is, the energy that they need to do this transition from T2G to Eg, the energy required, they absorb light in the region of visible light, and then they can do this transition. So the compounds of transition metals are, in general, they are colored. Okay, so there are two conditions which make them colorless. The first condition is completely empty d orbitals, which makes sense because, so let's say that the d orbitals are split into two categories, Eg and T2G, but there are no d electrons, so therefore no electrons to jump from T2G to Eg. So therefore completely empty d orbitals, they are colorless. Those species which have completely empty d orbitals, they are colorless. Second category is completely filled d orbitals. Okay, In the case of completely filled d orbitals, so what's going to happen? All the orbitals are occupied. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So since all the orbitals are occupied, so there is no vacant d orbitals for promotion of electrons from T2G to EG. So therefore again this case also they are going to be colorless. So there are two cases which leads to a transition metal ion being colorless. Now coming back to the question, we have been given 4 pairs, so I will write down those pairs. So we have been given scandium plus 3, titanium plus 3, okay, manganese plus 2 and chromium plus 2, copper plus 2 and zinc plus 2, nickel plus 2 and titanium plus 4. Okay, so we know the configuration of scandium is 3d1 4s2, configuration of titanium is 3d2 4s2, configuration of manganese is 3d5 4s2, configuration of chromium is 3d5 4s1, configuration of copper is 3d10 4s1, configuration of zinc is 3d10 4s2, configuration of nickel is 3d8 4s2, configuration of titanium is again 3d2 4s2. Okay, and here we have to remove 3 electrons, so therefore ultimately its configuration will be that of the argon, right? So basically 3d0. In titanium plus 3 the configuration will be remove 3 electrons, so we'll be left with 3d1. In manganese, if we remove 2 electrons, we'll be left with 3d5. In chromium, if we remove 2 electrons, we'll be left with 3d4. Copper plus 2, if we remove 2 electrons, we'll be left with 3d9. Zinc plus 2 will be left with 3d10. Nickel plus 2, 3d8. Titanium plus 4, again, argon, or you can say 3d0. So we can clearly see that, first pair, second pair, third pair, and fourth pair. First pair mein this guy is not going to show color. Okay, so they are asking, okay, in the question they are asking number of pairs from following in which both ions are colored. So both ions should be colored. So therefore, this is not considered. In second pair, 3d5, it has unpaired d orbitals which can jump. Even 3d4 has them, so therefore second is considered. In the case of third, we have 3d9 which can show color, but 3d10 cannot because 3d10 completely filled, so therefore this third is also not considered. And then we have 3d8, yes, this can show color. 3d0, again it cannot show color, there are no electrons to jump, so therefore this also, both the ions cannot show color, so therefore we have only one pair in which both of them can show color, so therefore statement 1 is false. Okay, so this is a false statement. Now coming back to statement 2. In statement 2 they have given us ions, 4 ions, and they're asking us the strongest reducing agent. Okay, cool. So we should know that oxidation is loss of electrons, the process in which there is loss of electrons. Reduction is gain of electrons. Okay, and oxidizing agent will do the exact reverse, that is it gains electron, and reducing agent, it loses electron. Cool. So now we will write down the configuration of all the 4 species that they have given us. So they have given us cerium, europium, gadolinium, thorium. Okay, these 3 are lanthanoids and this is a actinoid. Okay, so the configuration of cerium is 4f1, obviously there is a xenon core, 4f1, 5d1, 6s2, so this is for cerium. The configuration of europium is xenon core, 4f7, 6s2. The configuration of gadolinium is again a xenon core, 4f7, 5d1, 6s2. Okay, so in the question they have given a species, so they are talking about Ce plus 4. The configuration of Ce plus 4 will be, so we remove 4 electrons, so it will be 2 gone from here, 1 gone from here, 1 gone from here, so we are left with a xenon core, just a xenon core. Cool. Then they have given us europium plus 2. In europium plus 2, you can see if you remove this 2 electrons, you will be left with xenon core and a very stable configuration of 4f7. So xenon core and 4f7. In the case of gadolinium, they're talking about gadolinium plus 3. So we have to remove 3 electrons, so we'll be again left with a xenon and a 4f7 core. So xenon and 4f7. And lastly, coming to thorium. So thorium is an actinoid and its configuration is a radon core, 6d2 7s2. So thorium plus 4 will be, so we remove these 4 electrons, a radon core, right? So just looking at their configurations, xenon seems stable, europium also seems stable, gadolinium seems stable, and thorium also seems stable. So therefore configuration is not the only factor to decide if someone is going to be a reducing agent or a oxidizing agent. It depends upon the most stable oxidation state, and most stable oxidation state also depends upon other factors, for example ionization energy. So we can theoretically say that okay, Ce plus 4 is able to form Ce plus 4 because it occupies a xenon core, but we have to talk about the energy considerations also. It is very tough to convert cerium into cerium plus 4, right? Because you have to remove 4 electrons and it is not easy to remove those 4 electrons. So therefore ionization enthalpy also comes into the picture. So in general, we should know that the typical oxidation state of lanthanoids, or the most stable oxidation state of lanthanoids, is plus 3. The typical oxidation state of lanthanoids is plus 3. So this is the most stable state for all of them. They also show plus 2 and plus 4. Okay, by some of them. Okay, I will explain why. And these are shown by those guys, shown by those guys which, by losing 2 or 4 electrons, you can see that's why plus 2 and plus 4, acquire a stable configuration of either F0, F7 or F14. Okay, yes, the most stable state for them is plus 4, but they also, few of them show plus 2 and plus 4 because upon losing 2 or 4 electrons, they acquire a stable configuration of either F0, F7 or F14. F0 is, a noble gas core. F7 is exactly half filled. F14 is completely filled. So for example, europium plus 2. So to support our statement, for example, we have europium plus 2. Okay, so europium plus 2, the configuration is xenon 4f7. You can see it is exactly half filled. And for one more example is cerium plus 4, which is xenon and 4f0. So it has a xenon core, right? Okay, so yes, they do show plus 2 and plus 4, but as I mentioned, the typical oxidation state or the more stable oxidation state of lanthanoids is plus 3. So each case, they revert back to the more stable oxidation state of plus 3, either by loss or gain of an electron. So both of them will revert back to plus 3 oxidation state because that is more stable. Okay, now for example, Ce plus 4, it's a good oxidizing agent. Why? Because it gains electron to revert back to Ce plus 3. So it is a good oxidizing agent because it gains 1 electron and reverts back to Ce plus 3. It forms Ce plus 3. Okay, europium plus 2. Okay, it's a good reducing agent. Why? Because it loses electron to revert back to more stable europium plus 3. Okay, so europium plus 2 is a good reducing agent because it loses its electron to revert back to the more stable europium plus 3. So cerium plus 4 is a good oxidizing agent, europium plus 3 is a good reducing agent. Now gadolinium plus 3, so as you can see, it is already in the plus 3 oxidation state and it is exactly half filled, so it won't act either as reducing agent or as oxidizing agent. Okay, and coming to thorium, the dominant oxidation state of actinoids is also plus 3, but the difference with lanthanoids is that actinoids show a large variation in oxidation states. Okay, so thorium plus 4 will be a good oxidizing agent because, as I said, since plus 3 is the more stable state, so it will revert back to plus 3. To do that, it gains an electron, so therefore it is a good oxidizing agent. Okay, so thorium plus 4 is also a good oxidizing agent. So Ce plus 4 is oxidizing agent, europium plus 2 is reducing agent, this is neither, and thorium plus 4 is again an oxidizing agent. In the question, what are they asking? They are asking us the strongest reducing agent. So the strongest reducing agent is europium plus 2. Okay, and thorium plus 4 is oxidizing agent, cerium plus 4 is oxidizing agent, gadolinium is neither. Okay, so even statement 2 is false. So therefore both statement 1 and statement 2 are false. Okay, thank you.